Hi, hello, welcome back to our channel. Today we are going to discuss about semiconductor devices. Before this topic, we have to go through that matter exists in nature three states: solid, liquid and gases. Based on that intermolecular forces, solids are classified into two types. One is the crystalline solids, another one is the amorphous solids. What are the crystalline solids? Here each and every molecule and atom is following the regular manner. This is called the lattice. This is called the lattice, and these are called the anisotropic properties. Means what are that? Either refractive index, elasticity, thermal properties, all are different for different directions. That's why these are called the anisotropic bodies. Then these are having the sharp melting point. You can take the examples of like sugar, calcite and some crystals also. We can take the examples of this. First one is the crystalline solids. Then we are going to discuss about the amorphous solids. What are the amorphous solids? These are not having the particular shape. Like you can take some wheat powder, like a rice powder. You can say that those are the solids, but there is no particular shape and dimension for that. But these are called the isotropic. Why? All particles are having the same properties like refractive index and thermal properties of matter, elasticity. All particles are having that same properties. That's why these are called the isotropic, and these are not having that much sharp melting point. So based on that intermolecular forces, we are dividing into two types. Like that, based on the forbidden energy gap and based on the electrical properties, solids are classified into three types. What are those? First one is the conductors, second one is the insulators, and third one is what? Semiconductors. Our chapter name is the semiconductors. And before that, what are the conductors? The substances which can allow the electricity through them. Those are called the conductors. Like iron, all metals are belongs to conductors. Here free electrons are available. But when we can go through the insulators, there is no available of free electrons. There is no passage of the electricity through them. Those are called the insulators. Then our chapter name is the semiconductors. In that only meaning is there. Semi means it is in between the conductors, and it is in between the conductors and insulators. At 0 degree Kelvin, these are behaving like insulators. There is no availability of the free electrons. But at room temperature, these are behaving like the conductors. Why? What happened? Why? Because of what reason these are behaving like conductors at room temperature? Look here. So already I said, based on the forbidden energy gap. What is the forbidden energy gap? Forbidden energy gap, we can write it FEB also. Forbidden energy gap. Actually, there are three bands are there. One is the valence band. VB belongs to valence band, and this is the conduction band. The gap between these two is called the forbidden energy gap. Forbidden energy gap. Here valence band is either partially filled and completely filled. This is the highest energy level occupied by the electrons here. And this is either partial or empty, this conduction band, based on the nature of the materials. And here there is no existence of that electrons. This is called the forbidden energy gap. In this first we can go through the, in the case of conductors, no conduction, no forbidden energy gap. This is the valence band and this is the conduction band. Easily electrons are jumping from valence band to the conduction band. Like insulators, no, this gap is more. This is the conduction band and this is the valence band. But here 5 electron volts, we should observe that energy gap. Even we are providing some energy also, these electrons can't able to jump from valence band to the conduction band. So there is no available of the free electrons. Then next one is the, in the case, this is insulators, in the case of insulators. Then semiconductors. In the case of semiconductors, what happens? At 0 degree Kelvin, these are acting as a bad conductors or insulators. But here forbidden energy gap about 1 electron volts. So whenever we are providing that energy, these are jumping from valence band to the conduction band. Then here one vacancy is created and here one free electron is available here. So this is called the hole, and we can treat this is as a positive charge also, and this is the free electrons You know that it is having the negative energy. So in the case of semiconductors, we can treat both holes and electrons are responsible for electricity. So we can say that I equals to electron due to the current due to the electrons plus current due to the holes, also we can write it. This is about the semiconductors based on the forbidden energy gap. Now we are going to discuss about what are the semiconductors. What are the semiconductors? You know that, but what are the examples of the semiconductors? Germanium and silicon are the examples for the semiconductors. But when we can go through the types of the semiconductors, there are two types of semiconductors. One is the intrinsic semiconductor, another one is the extrinsic semiconductors. What are the intrinsic semiconductors? Semiconductors in pure form are called the intrinsic semiconductors. You can take the examples of germanium and silicon are the examples of the semiconductors. Then second type of semiconductors are extrinsic semiconductors. What are the extrinsic semiconductors? When we are doping the pure semiconductors, we are getting the extrinsic semiconductor. Why we are doping? We can increase the conductivity when we are doping the semiconductors. Then here also there are two types of extrinsic semiconductors. One is the p-type semiconductor, another one is the n-type semiconductor. When you will get p-type and when you will get the n-type semiconductor, we are doping that pure semiconductor with third group elements. Then we are getting the p-type semiconductors. When we are getting the n-type semiconductors, when we are doping with pentavalent or fifth group elements, we are getting the n-type semiconductors. Okay, but in the case of p-type semiconductor, look here, p-type semiconductor we are doping with, you know that germanium or silicon or semiconductor is tetravalent. See, 4 valence electrons are there. Whenever we are doping with third group element, then what happens here? Here one vacancy is here. This is for single atom. When we are taking that quantity of matter of this germanium, each atom one vacancy is there. This vacancy we can call this hole also, and this charge is what? Positive charge. That's why in the case of p-type semiconductor, what are the majority charge carriers are the holes and minority charge carriers are the electrons. When we can go through the n-type semiconductor, see, we are doping with pentavalent. Look here, 4 electrons are forming that covalent bonds. Each atom one excess electrons are available. Excess electron is available. That's why what are the majority charge carriers in n-type? Electrons are the majority charge carriers and holes are the minority charge carriers. So these are belongs to p-type and n-type semiconductors. So now we are going to discuss about the junction diode. What is the junction diode? We are taking the pure semiconductor, and one side you are doping with p-type, another side doping with trivalent, another side you are doping with pentavalent, then we are getting the junction. So junction diode, look here, junction diode, and before that Fermi energy level also it's there. What is the Fermi energy level? The highest energy level occupied by the electron at 0 degree Kelvin is called the Fermi energy level. This Fermi energy level is nearer to the conduction band in the case of n-type semiconductor. Why? Majority charge carriers are the electrons. In the case of p-type semiconductor, this is nearer to the valence band. But in the case of pure semiconductor, it is exactly between that in the middle of that forbidden energy gap. So that is about the Fermi energy level. Based on that also we can say, is it pure semiconductor, is it n-type or is it p-type semiconductor. Then come to junction diode. Look, we are taking one pure semiconductor. One side we are doping with trivalent, means majority charge carriers are the holes. These are the holes. And another side we are doping with pentavalent. Here majority are the electrons, but minority 1 or 2 we can take it, here electrons and here. So whenever we are doping like that, here the some of the holes are diffusing in that, this side we are getting, and some of the electrons are diffusing this one. It will, this a part of this middle part of this junction diode is like, junction means it is neutralized. Then what happens, these holes can't able to go that side, these electrons are can't able to come this side, like traffic jam also we can take here. It forms a band here, that is called the depletion layer, and it is having the potential also. This is the VD, potential of depletion layer. We can take it, this thickness we can take it D or T also we can take it. Now this is about the junction diode, and this is the symbol for junction diode, PN junction diode. Now we are going to discuss about what is the forward bias, and what is the reverse bias. It is very easy. Here P is giving to the positive of the battery, then N is giving to the negative of the battery. This is giving to positive, this is giving to the negative of the battery. Then what happens? All holes are repelled by the positive charge and overcome this depletion layer. These are entering in entire material. Then what happens here? Depletion layer with this decreases. It is like switch on condition also you can say that. So whenever this potential is overcoming the potential of depletion layer, then automatically what happens? Current flowing to the circuit. This is called the forward bias. So you can remember that in the case of forward bias, we can decrease and it is dominated by the extra potential. This is called the forward bias. When we are drawing the graph here, this is the potential, this is the current. Beginning we are giving like 0 volt, 0.1, 0.2 like that. At that time there is no flow of the current. Whenever we are dominating this one, it is increasing current like this. This is called what? Forward bias. Then we are going to discuss about the reverse bias. What is the reverse bias? Just reverse of this one. P is giving to the negative of the battery, but N is giving to the positive of the battery. Then what happens? All electrons are attracted by the positive charge. Here all holes are attracted by the negative charge. Only minority charge carriers are moving. Then in this case you can say that depletion layer width is increasing. This is about the reverse bias. When we are drawing the graph between potential and current, we can observe that current is increasing in reverse direction, that too due to the minority charge carriers. This is about the forward bias and this is about the reverse bias. And what are the uses of the semiconductors? Our electronic devices like transistors, rectifiers and switchboards, all we are making with the help of these semiconductors. Then we are going to discuss about Zener diode. What is the Zener diode? What is the use of this one? In electronic devices, for controlling, for stabilizing that potential, we are using the Zener diode. It is used as a voltage regulator. But when it is useful, in the case of forward bias, it is like normal junction diode only, waste of cost. But when we are connecting, this is in reverse bias, it is having the sharp, this is having the sharp breakdown voltage, and it is using the as a voltage regulator. Voltage regulator means whatever the input potential, it is giving the constant output potential, that is called the Zener diode. Actually this is always connected. Zener diode symbol is like this. This is the Zener diode. How it is connecting in the circuit like this. See, this is giving to the reverse bias means it is negative, it is positive. In between we are taking one resistance. Across this we are taking one load resistance. Here we are getting the output, and here we should provide the input, and this is the series resistance. Here you can say that potential across this one is equals to potential across the junction diode, Zener diode equals to potential across the load resistor also we can take it. But current I equals to what we are taking here, the resistance is IR plus IL into resistance of this one RZ or RL also we can take it. So this is about the Zener diode. We can use it as a voltage regulator. The next one we are going to discuss about the rectifiers. What is the rectifier? It is an electronic device. It is converting alternating current to the direct current. But there are two types of rectifiers are there. One is the half wave rectifier, another one is the full wave rectifier. Half wave rectifier means meaning is there only. It is converting half of the alternating current into direct current. But in this we are using only one diode. See how it is, that circuit diagram. one diode, that too we are connecting in forward bias. This is the load resistor. Here we are getting the output. Here one input is there. This is the symbol for alternating current. See, yes, actually input in terms of the waves we can say that positive pulse, negative pulse, like this. This is the input. But output, you look here. When this positive pulse is coming, this is acting as a forward bias. It is converting alternating current to the direct current, like that. But whenever negative pulse is coming, it is acting as a reverse bias. There is no conversion of alternating current to the direct current. Then once again we are sending this second one, here some gap, like that. Only half of the alternating current is converting into direct current. This is called the half wave rectifier. And you remember that efficiency of half wave rectifier is eta equals to 0.406 RL by RL plus RF. RL is the load resistance and RF is the forward resistance, you can take it, and 0.406 means this efficiency is in terms of percentage 40.6%, you can take it. And one more thing I want to say to here depletion layer is there, no? Here we can you can use that intensity and potential formula E equals to V by D. With the help of this you can find out depletion layer potential, thickness of this one, and intensity of electric field. All these three terms we should apply and we can find out whatever based on that given data. Then this is the efficiency of half wave rectifier. Like that full wave rectifier, how to find out? Full wave means in that only meaning is there. It is converting alternating current to the direct current. You can say that is called the full wave rectifier. But what is the difference here? Here instead of one diode we are using the two diodes, center tapped here. This center tapped we are giving to the earth connection. But here we are using one more diode. This is the D1 and this is the D2. When positive pulse is coming, it is acting as a forward bias. We are getting output. When negative pulse is acting, it is as a forward bias and it is reverse bias. So complete alternating current to the direct current. This is called the full wave rectifier. But efficiency is what? 2 times of this one means AM formula. But here you are getting 812 this one, and here that efficiency in terms of percentage we should write it 81.2%. So there are 2 types of rectifiers. One is the full wave rectifier, another one is the half wave rectifier. You must remember these formulas. So chances are there to get the problems based on this. Until here E equals to V by D, and here the current is responsible for both holes and electrons in the case of semiconductors. Then we are going to discuss about the transistors. This is the 3-layered semiconductors. How we are getting this one? When we are taking 2 junction diodes, we are connecting back to back. Back to back we are connecting, then we are getting the transistors. Transistors also 2 types are there. PNP transistor, another one is the NPN transistor. It is having the 3 parts also. See, when we are going through the transistors, PNP transistor, look, this is the PN junction diode and this is one more PN junction diode. Then when you are connecting these, we have to reverse the second one, we should connect this one. Then what we are getting? PNP transistor. This is first part is called the emitter, base and collector. This emitter is heavily doped, this is the base is lightly doped, this is the moderately doped. And you remember that collector size is more comparing with emitter and base, but base is very like a thin, like that you can say that. Here you can write this formula, emitter current equals to base current plus collector current. And NPN transistor, how to get the NPN transistor? We have to reverse first one, then you are getting, this is the NPN transistor. Here this is the emitter, this P type is the base and this is the collector. So there are 2 types of transistors, and always you remember that this junction is called the emitter junction and this is called the collector junction. This is the collector junction. And one more thing, we have to connect these transistors in 3 configurations. Common base also you can take it, common emitter also you can take it, common collector also you can take it. And at the same time, in the case of PNP transistor, you can show like this. The symbol is like this. This is the base, emitter, and this is the collector. And here arrowhead is towards the base. Like that in the case of NPN transistor, we can show like this. This is the emitter, base, and this arrowhead is the towards the emitter. So this is the NPN transistor and this is the PNP transistor. Then how these three configurations look here. If the base is, if the common base means emitter, base, collector, we can connect. Base is common for both input and output. Both input and output. Suppose common collector means we can take it. See, this is the base, this is the emitter, and this is the common for both input and output. Base as usual we can. Like that common emitter means we can take it. This is the emitter, this is the base, and this is the collector. This is common for both input and output. Like that we can take it. So there are three configurations in the case of transistors. But in the case of common base, suppose we are taking common base transistor. Common base transistors. Common base transistor. So base is common. You can take here like this. This is the base, this is the emitter, and this is the collector. This is common for both input and output. Here current multiplication factor, it is represented by alpha equals to delta IC by delta IE we are taking. This is the alpha. This is what common base transistor. Like that common emitter transistor. Common emitter transistor, current multiplication factor we are representing with beta. Beta equals to delta IC by delta IB we are taking. So this is the common emitter and this is the common base, and we can give the relation. Always you remember that alpha is less than 1, beta is in between 20 and 200, in between 20 and 200. So you can give the relation between alpha and beta also. Alpha equals to beta by 1 plus beta, and beta equals to alpha by 1 minus alpha, you can take it. These are the relations. Like that in the case of common emitter resistor, you can take it R resistance output, and this is the resistance input. You can get the resistance gain equals to, you can get it R output by R input, you can take it. Like that voltage gain we can take it. Current gain into this resistance gain, we can take it delta IC by delta IB to R output by R input. Like that power gain what we are taking, B square in beta square into R, you can take it R output by R input. These formulas you must remember because they will mention in that question common base. Common base means immediately you can go through the alpha. Common emitter means you can go through the beta. Many people are thinking they will confuse, they won't read the question. Current multiplication factor means sometimes they are taking alpha, sometimes they are taking beta. So don't confuse here which is the common base, we are taking alpha. Common emitter we are taking the beta, and with the help of this we can calculate the power gain, voltage gain, and resistance gain also. So this is about the transistors. In next class we are going to discuss about the logic gates. Please subscribe my channel and share to your friends also. Thank you everyone.